Hi, I think we're right on time. Please welcome Zsolt Parragi from Percona, who's going to do a technical presentation on the PGTDE encryption extension to PostgreSQL. Zsolt is joining us from sunny Portugal and is going to focus on the technical aspects of this extension and these efforts. Please welcome Zsolt.
So hello everyone, I'm Zsolt Parragi. In the past few years I worked on our encryption solution for PostgreSQL, and that will be the topic of my talk. We choose to implement it differently than the previous efforts in Postgres and the way it is usually implemented in most database servers. So I think this could be an interesting talk for everyone. It will be mainly about our story, what we did, how we did it, why we did it, what we did correctly, what mistakes we did. So it's like a retrospective, and I hope that everyone can learn something about our choices and about the things we did. So TDE itself is transparent data encryption, and the idea is that we want to encrypt the data before it's written to the disk. It's about only encrypting storage, about what we store on the disk, and usually it doesn't mean that we encrypt anything during the operation of the server, like everything that stays in the memory, that's usually still unencrypted. And we want to provide this service without any visible changes to the user. Of course, there has to be some changes like configuration and telling what we want to encrypt and things like that. But other than that, our goal is that the user doesn't have to change the way they write queries. The application works as before. The only difference is that now we are writing data in the encrypted format to the disk. And it's already available in most SQL databases, and it's quite often a policy requirement, like my colleague Jan talked about this yesterday. In the financial sector, this is basically a requirement for anyone in 2025. But even if it's a requirement from a policy standpoint, there are still many debates about this. For example, technical people like developers often question if it's even worth it to implement. Because we already have encryption at many levels. Like we have application level encryptions. Postgres already have several libraries and possibilities to do this. We have disk level encryptions on file systems. Linux and Windows both support this. And even if we encrypt the database files, as I said, the memory usually remains encrypted. So we still only encrypt data on the disks, and this has a very limited use case if the disk is already encrypted. But of course, there are use cases where we can't encrypt the disk. So there are many questions about this. Not everyone agrees that we need to have this feature, but it can be useful in some cases. And another technical question about it is that if we add features to the core logic, that usually means some amount of performance loss, even if people are not using this feature. So often people are concerned that, yes, we can implement encryption, but if we do that, then everyone will notice some performance degradation because we need new abstractions, new conditions, and so on. Even if it's just 1% or 2%, it's there. And another part of the typical debate is choices. Like, encryption is not a single easy topic. We have many difficult decisions to make there. Like, there are lots of encryption algorithms, key sizes, many libraries that can help us implement encryptions. We also have to decide which files we want to encrypt and which files is okay if we leave it unencrypted. Either initially and then we add support for them later, or maybe we don't want to encrypt them ever because it's not really important. We also have to decide when to encrypt something. Like a database server is a huge, complex software. It has many layers, many components, and there are several places where we can add the encryption code. And actually, there are different solutions available today for different software which choose different approaches in this. And we also have to make the decision if we want some simple checkbox item, like I want to turn on encryption and that's it. There are no other choices. Or if we want to make this heavily customizable with tons of settings, like which table to encrypt, what key to use to which tables, where to store the keys, like I want to store the key for this table there and want to store the key for that table there. How we want to change the encryption key, do we want to also control permissions with the keys, and so on. There are lots of choices here. And this is kind of the elephant in the room. TDE is a really difficult topic because we have to make these choices. And PostgreSQL is a community-driven project, but which is really great. People have really great discussions about how we have to implement things, what's a good idea, what's a bad idea, what approach we have to take. There isn't a single decision maker anywhere here. And the first step we have to do is that we have to agree the way we want to implement TDE, what we want to do exactly. And this is kind of why TDE is difficult in Postgres. The first patch was actually submitted to the hackers list in 2016. It was a simple implementation compared to what I mentioned just about configuration, like it was cluster-wide with a single key and so on. And then in the years, it got some improvements, like it was users were able to to configure it in a table level. It got better key management later. It became a really huge patch, and people kept discussing it because they disagreed about parts of the patch. And even this year, we have no consensus about it. The discussion kind of stopped because people either lost interest or went to try different approaches or decided that, yeah, we won't be able to solve these questions. So there's not much progress there anymore. We, of course, also have a closed source enterprise PostgreSQL forks, and many of these actually implement encryption as additional features on top of the community version of the PostgreSQL, but these are not open source. So you have to pay some company and receive their products to use these encryption features. These are specific to that product. And there's a different approach that currently maybe more active in the hackers list is that people try to make smaller changes that are not directly encryption related, but they would do refactorings that would make implementing encryption or part of the encryption process better. Like there are discussions about a unified file system API, or about transparent column encryption, or special page storage where we could store additional metadata for the database pages and so on. These are just 3 examples. That there are more discussions, but even these progress slowly. So this is why we asked, can we provide an open source version of an encryption solution for PostgreSQL? So we wanted to do something that's available for everyone. And one choice for this is, of course, that we could also create a fork, but keep that open source. Either maintain the already existing patch set, which is already there. It was just kind of abandoned. It isn't updated for a few versions now. Or we could create a completely new but similar patch set. But the problem with this is that this is a huge patch set. Even rebasing it on the current version of the Postgres code would take lots of efforts, and then we have to maintain it. It's a constant struggle. It would take up lots of resources from our end, and it would mean that we would significantly diverge from the mainstream community code. So instead of that, we asked a different question. Since Postgres also has this great extension ecosystem, can we do the same thing with an extension? Ideally, without any core changes, just using the already available extension points in PostgreSQL, or if we can do that, maybe we could just add additional extension points so that we can implement encryption in a better way. And first, of course, we wanted to try the first of these choices, because it would be really great if we could develop something that works out of the box with everyone's Postgres installation without any changes. And to do that, we looked at something called access methods. This already exists in PostgreSQL. Basically, this is how both tables and indexes are handled internally. So anytime Postgres has to access a table or an index that can be reading or writing to it, it goes through this feature called access method, which can be extended using extensions. Extensions can define new access methods. Internally, even if anybody just creates a table, it implicitly creates a table using an access method, which is called heap, the default access method in PostgreSQL. But there are other extensions like Citus provides its own access method. TimescaleDB also has one. There's also OrioliDB. And of course, there are many more indexes that also provide, like, I think many people use custom indexes for PostgreSQL, like Postgres and other things that provide custom index implementations. So this is something that's already there and usable. So we started thinking, what if we just duplicate the internal default access method heap, we copy it to our own repository, and put it into an extension. We basically do a search and replace it, rename heap to TDE heap, and we just add minimal modifications to it, so it encrypts the data before it writes it, and decrypts the data when it reads it. That should be simple and easy to do. So we did a proof of concept, and that was really easy. We got it working in just days, and it was able to execute simple queries, like simple select, simple insert, updates. It all worked. And at that time, we had to ask ourselves the question, did we just succeed this easily? Could be this simple? And of course, we knew that there were open questions, like we just duplicated one single access method. So of course, that means that we did not support the other access methods I just mentioned. And we also completely ignored the question of indexes, because indexes use different access methods, so we would handle those also in some way. But before we go there, let's talk about how our implementation exactly worked. So PostgreSQL stores data in tuples, which is a really simplified way, just database rows. So basically, we hooked into this part of the heap access method, and we added a decryption code anytime we read a tuple, and we added an encryption code anytime we write a tuple. And the interesting thing about this approach is that the entire thing happens in a single connection handler. So when a connection has to access a specific database row, it goes into the more internal parts of Postgres and says that I want to decrypt that row. And when it has to encrypt that row, it already says the other levels of the Postgres internals that we want to encrypt that row. And Postgres has many other components, like the buffer pool example, where it caches the data internally. And that means that all these lower level components store the data in an encrypted form. So earlier, what I mentioned, that most encryption solutions only encrypt the data on disk and keep everything in the memory in a plain text format without encryption. Our solution was actually better, because it only decrypted the data for a very short time when it actually had to access that database row. And immediately after it had no need for that database row, it forgot about it. It discarded the decrypted data. Of course, this caused some memory management questions, because we had this question, where do we store this decrypted data? As I already mentioned, we decided not to decrypt in the buffer pool, because that would have been one solution to kind of, when we just read the pages from the disk into the buffer pool, and every time we have to access a database row, we decrypt that row, and then after that, the buffer pool would store that row in a decrypted form, but everything else would stay there in an encrypted form. But this would have required more modifications in the buffer pool logic and so on, and we wanted to avoid this. So this is why we chose this approach, where we only kept the decrypted data in the local actual connection process. And this worked because most of the queries actually only work on a single row at a time. Like, they read one row from the buffer pool, try to encrypt or decrypt it, try to read it, see if they have to use it or not, and after that, they either write a modified version it to disk, or just completely forget it and go to the next row. So this worked quite simply. But the problem is that I said most of the code. Sometimes, of course, it is not true, because we have complex queries like selects with many joins, and we can also have updates or other statements with subqueries and other complex features that work on multiple tables. And in this case, it's possible that the Postgres has to work with multiple database rows at a time. And this is when we discovered that some cases we have data corruption. We had no issues with selects and read-only queries. The problem was when we started to modify database rows. Our approach didn't work correctly. So we just had a really quick fix, which was that we, instead of immediately forgetting about tuples, we decided to keep the decrypted data until the end of the statement, because this was a really simple way of trying it and hiding the problem. The problem is that this works very nicely for small queries, but let's say that we have a table with 20 gigabytes of data, or maybe terabytes. If we do a sequential scan on the entire table, and we keep all decrypted records in the memory until the statement ends, that means we have to keep the entire table in the memory, which causes huge memory spikes. And of course, it's plain impossible for really big tables. So we had to find a better approach. Fortunately, after looking into the heap code more, we discovered how this works internally, and were able to provide a solution which only required decrypting one row for each participant in the query. So like, for example, if somebody has 10 joins, then we had to keep 10 rows decrypted in the memory, which was a more acceptable solution. And after that, we also during that, we had another question, of course, which is, how good is our solution performance-wise? I talked already about that we had this memory spike problem, which we tried to solve, but what about what about just the execution time of the queries? So at first, we used simple performance tests, but everyone uses, like pgbench and sysbench and other simple test scripts like that. And these seemed all really nice. We only had a few percentage of performance drop. It was actually better than we expected. But then the thing is, we didn't have index encryption. And all those basic tests that people usually use for testing the performance of databases use index scans. So actually, very little time of those tests is spent on reading or writing actual database rows. Most of the time is spent in indexes. And because of this, after a time, we tried sequential scans and realized that we have a terrible performance drop there. Because if you have to read every record and you decrypt everything in small batches instead of entire pages, that takes up a lot of time. And then we also had to allocate memory, free memory, so on. It had lots of overheads. And we were able to improve this significantly. Like, after some trials, our code became like 3 times faster than the first version. But that still meant that we only had around 60% of the normal non-encrypted performance. And when other commercial solutions advertise a 10% performance drop, it's not great if your solution has 40% performance drop. That's significantly lower there. But we also had no idea how to improve this further than this. And since I already talked about indexes related to the performance, we still had this open question: can we handle indexes or not? And if we handle all the index access methods which are internal to Postgres, so it's part of the core or the contrib module, what about other extensions like PostGIS? How will we handle them? Do we fork PostGIS and provide our own encrypted version, or what can we do? And we also had serious performance concerns, because so far our performance, if users used index scans, which is the typical use case, was quite great, but only because we didn't encrypt indexes. So we had to question, if we also start encrypting indexes, how much performance drop we will see with index encryption. Will we get the same 60% of normal performance? Because if we do, that's a serious concern for anybody who wants to use our solution. And we also had some security concerns because we took some shortcuts about which parts of the data we actually encrypt in the files. We didn't encrypt everything, only where the meaningful part of the data were. And for indexes, even if you can only see the structure of the file, that could reveal some information of the data. So we weren't sure if this solution would be enough for that. And considering all these issues, we decided to call this a dead end. We had these performance problems. We were quite sure that we won't be able to solve them. We also had questions about correctness, because I already mentioned that we discovered some corner cases where we had data corruptions. And initially, we thought that modifying heap will be simple because we only have to change a few places. But in time, we discovered that we had to change more and more things there. And that made us question ourselves, what if we missed something? What if we discover a data corruption bug later when it's already there in the data, in people's databases, and we actually corrupted real-world data? That would be quite bad. And then, yes, the question about indexes was also there. So we decided to try a different solution. Going back to my previous slide, we still wanted to do it as an extension, but instead of without core changes, we started to look into where we could add additional extension points into the core, so we could implement our extension in a better, nicer way that would be safer and better performing. And that is where we started to look into the storage manager, which is kind of an additional, already existing extension point in Postgres. It's basically the layer between the buffer manager and the actual disk storage. When the buffer manager has to load a page from the disk, it tells the storage manager that I want to load that page. And when it has to write a page to the disk, it tells the storage manager to write that disk for the page. And it works for all database objects. It was already designed with extensibility in mind, but that was before Postgres introduced the current extension ecosystem. It's from the quite old days. So it's actually not exposed to the current extension system. But there was already a patch on the hackers list created by Neon about making this extensible. And as we discovered in the process, there are other companies using this patch, even if it's not accepted into the core yet. So this was a perfect opportunity for us, because that means more people are using it. So there is a good chance that we can get this into the core, so it's available for everyone. And as I said, it's also the storage point for database objects, generally. Tables, but also indexes, which we weren't able to encrypt previously, and anything else there in the database, like sequences or user functions, or anything visible in the database. But database objects also means that there is a limitation, because the write-ahead log doesn't go through the storage manager, and temporary files also work differently. So that means that if we are using the storage manager, we are not encrypting those. So with this in mind, we decided to add these extension points. First, we took the existing storage manager patch and created our fork with it, and then we added similar extension points to the wall. And in the future, we also plan to do the same thing with temporary files, but we didn't go there yet. And this means that we had core patches, but these were minimal, only a few hundred lines of code, so it's easy to maintain. We also decided to reuse everything we can from our previous solution. For example, in the previous solution, we used access methods as a marker for encryption. We created this TDE heap access method, and the new solution didn't have a need for an access method, but we decided that this is still a good marker to see which tables are encrypted and which tables are not encrypted. So we kept our access method and said that everything that uses TDE heap, that's encrypted. Everything that doesn't use it, it's not encrypted. And in reality, TDE heap had no changes compared to heap. It was the same heap storage engine as originally. And for indexes and other things, if they belonged to an encrypted table, we said that they will be encrypted. If they belong to a normal table, they won't be encrypted. So we kept, and we also kept the complete user-facing API as before. So like how you create the keys, how you configure encryption, everything stayed the same as before. Because this helped us create a prototype quicker. Using these shortcuts, we again were able to finish everything in a few days. We had a working prototype. We were able to execute queries. So we had the same question as before. Is this success? Did we succeed? Or will we face similar very bad issues as we did previously? And of course, we had some challenges. One of the first challenges, even during the first days of the implementation, was that with the storage manager, we are kind of at the wrong abstraction level. Because with the table access methods, we had access to every database, to every information a database object can see. So we were able to make decisions based on that. But the storage manager works at the storage level. It doesn't know about database objects or anything at all. So we needed some way to decide if we have to encrypt a file or not, because we only know about files there, not tables. We had this file name. And for that, we decided to use event triggers, which is also existing feature in Postgres, maybe less known than normal triggers, but it's there. Basically, normal triggers work on data modification statements, like you can add the triggers for an insert or an update, while event triggers work on data definition statements. We can add the triggers for a create table or an alter table or other DDL statements. And with this, we were able to add the triggers around these statements. And because these triggers have access to the database information, we could check that, do we have to encrypt this table? Or do we have to encrypt this object? And if yes, we could set some global variables inside our extension, and all the file writes or all the file writes happening during this statement were able to decide that they have to write encrypted data based on this. And this worked all well, but there's this problem that in Postgres, sometimes we are simply rewriting the database file. For example, if we execute an alter table that completely changes the data format, what Postgres does internally, that it creates a file with a new file name, copies all the data into the new file with the new format, and after it's done, it deletes the old file. And this is not a problem with things like alter table, because alter table is a DDL statement, so we have an event trigger for that. We can handle this in the event trigger. But we have other statements that do this, like vacuum full. Vacuum full is not a DDL statement, because it doesn't change anything in the data format. It just vacuums the table. But because it's not a DDL statement, there is no event trigger that gets triggered when users execute a vacuum full. So what we discovered is that if somebody executed a vacuum full, suddenly we started writing plain text data in a file that should have been encrypted. And I'm not sure if this was a good or a bad thing, but our code actually worked. It properly detected that the file is plain text and nothing crashed. Everything worked. The problem was that suddenly a file that should have been encrypted was plain text on the disk. And we actually didn't notice this problem for some time because we actually have to check the file and see that it's not encrypted there. So after we added some sanity checks there, we actually had to add some more code patches to our minimal patch set so that we are able to handle situations like this. But fortunately, it was all solvable. And there's also another interesting corner case is that Postgres has some nice advanced features where tables are grouped together based on some features. There are partition tables which are present in basically every database server, but Postgres also has table inheritance, and it also has typed tables. And if somebody is using these features, it's possible that for example, we have a partition table where one partition is encrypted and another partition isn't encrypted. Or if somebody has a typed table, it's possible that somebody creates an encrypted table based on the type and another unencrypted table based on the type. And then when they execute alter table statements, these alter statements can be executed on the top-level objects, which means that in a single statement, we are altering or changing multiple tables. And our event trigger code works that basically at the start of the statement, we try to decide if we have to do all writes in an encrypted or a plain text form. And if we are changing multiple tables in a single statement, and some of them are encrypted and some of them are plain text, we can't make this decision because we would have to write something in an encrypted form and something in a plain text form. That's not possible in our architecture. And actually, we weren't able to come up for a good solution for this. But fortunately, this is a very rare and specific use case, so we decided to just report errors for this instead of corrupting the data or accidentally writing plain text record for things that should be encrypted. Because in every time, it is very easy to rewrite these statements differently so that they only work on parts of some of the tables at a time, and then everything will work out correctly. And after that, we started to look into a different topic, which I already mentioned earlier, which is vol encryption. Vol encryption actually wasn't an issue in our first prototype, because our first prototype worked on tuples, and when we wrote records to the disk, to the buffer pool, they were already encrypted. And this meant that when we were writing the vol, we already wrote encrypted data in the vol. And when we did recovery, we again had no issue, because all the recovery had to do is to copy the already encrypted data from the vol into the table file. But with the new approach, this was no longer possible because vol works completely differently, and we had to add extension points for it. So these extension points again had the same issue as our storage manager extension points, that we added a similar thing there. Basically, every time we are writing a vol page or reading a vol page, we can call our encryption or decryption code. But this means that we are again at the wrong abstraction level, because we are dealing with vol pages, and we have no idea about the vol internals there. We just have like 8 kilobytes of data there. We can say that this part of the data is an encrypted table, and this part is a plain text table. We can't choose what to encrypt. We have to encrypt or decrypt everything. So we had to make this a separate setting. And this is actually not a terrible thing. Basically, every database server works this way. We were just really happy that our initial solution was better than this, but now we basically had to go back into this approach with a separate setting. And there's another interesting thing here, which is that vol is sometimes rewritten. Most people think that vol is a write once, read often type of thing. It's our safety net. So we write once, and then we read it back when we have to, because of replication, because of a crash, or because of something. And it never gets rewritten ever, because it's our source of truth. It never changes. And because of that, we made this simplification that we always try with the latest encryption key. Because, of course, users can change their encryption key so that they write with a different key. And we just assume that even if we change the encryption key of vol, and we had multiple keys in the past, we can always use the latest key for writing. Yes. Of course, there are some corner cases. Especially with replication, it's possible that sometimes we have to rewrite old data. In practice, we are always rewriting the same old data, so it never changes. We never write something different to the vol, and that's great. But the problem is that if we change the encryption key in the meantime, and then we rewrite all the data using the latest key, which shouldn't have been used there, then we get data corruption. And this was a debugging nightmare, because, of course, the error happens during the write, but we only notice it if we ever have to read back those vol records that we wrote with an incorrect key. So this was something that took us for some time to figure out. It took us some time to find it, and then it took us even more time to figure out what's happening there exactly. And there's one more problem with the vol, which is the tool ecosystem. In the previous solution, we kept the vol file as is. We just wrote encrypted tuples into it. Now, with the new approach where we are writing entire vol pages encrypted, that means that tools like PG voldump or any backup tool that tries to do something with the vol no longer works, because they expect vol to be in a certain format with proper headers and so on, and that's no longer the case. We have, from their perspective, completely random data there. So to solve this, we actually had to fork some of these tools. For example, instead of PG voldump, we now have PG TDE voldump, which understands encryption. The normal PG voldump can't work without vol encryption because it doesn't see the proper data there. And this is where we are currently. We still have lots of things that we have to do, like we want to upstream our extension points. We want to implement temporary files because, as I said, we just ignored it. We want to add support for encrypting system tables, including tables created at initialization time, which is not yet supported. And with PG18, we just discovered that we have a nice problem of AIO. With PG18 right now, we only support if the user disables AIO and uses synchronized reads. And we also have some remaining interesting questions. And these are all related to our decision of keep the existing code. For example, I mentioned that we decided to keep the table access method as a marker for encryption because we already had that. This was the source of many of our problems, and we realized that maybe we could better by using table spaces. So say that this table space is encrypted, that table space is not encrypted. We are not 100% sure that this is a better solution. We are still thinking about it, but it might be better. So if anybody has an option, we are really interested in that. And we also have a question about multi-tenancy, because this was a really important focus in our original solution. We try to implement things in a way so that we keep everything in an extension, everything within a database, and every database owner in a Postgres installation can set up encryption completely differently and independently, which is ideal for some shared hosting and similar situations. The problem is that this was a great feature in the first prototype, and we kept it because, one, it's a great feature, and two, we kept the user-facing API as it was originally, and it had this feature in it. The problem is that now vol is global. We encrypt the entire vol file, and a single vol page can contain data from multiple databases. So it's not really multi-tenant. And it's also a problem because previously, we didn't have to interact with recovery because all recovery did is copied the already existing encrypted data from the vol into the database file. But now vol has a different encryption key than any of the databases. So recovery first has to decrypt vol, and then it has to write encrypted data to the different databases. So it also needs access to every encryption key for every database. And that means that in a multi-tenant setup, if for some reason we can't access the key of a single tenant, then recovery for the entire PostgreSQL server will fail. And that's not a new thing. So right now, any multi-tenant setup requires super user privileges as a safety measure so that somebody can't break an entire PostgreSQL cluster just because of this. So in summary, complex projects rarely go as you plan it. We had to implement multiple features, multiple prototypes, and all of our prototypes look good initially. But the first prototype, we learned some lessons where we discovered that we had unforeseen issues, so we had to abandon it. And the second prototype also had some issues, so we also weren't sure during the entire time that this will be the way to go. This is a good production-ready implementation, but it turned out to be the case. So right now, we are quite sure that it is something that works and something that people can use effectively and safely, but we still have lots of open questions and improvements that we have to make. But the key takeaways from this is that we shouldn't have delayed testing, or we should have been more critical about tests, especially performance tests. And I think this is a mistake that people often make, that we were so happy that we got something working and we were able to do basic tests with it, that we kind of forget that we have to do more and more through testing and verification that our ideas really work the way they should be. And the other takeaway is that you shouldn't be afraid to change things. Many of our current issues are all related to the fact that we decided to keep code from our first prototype. It wasn't a perfect fit for our second prototype, but it was already there, it was easy to use, and we were able to get our second prototype working quicker thanks to them. But in the long run, we are quite sure that these weren't the best decisions we made. So we will have to do additional work around refactoring them and making them better. So I hope that these findings can help others to do better in their projects. And thank you, and if you have any questions.
Here you go.
I'm sorry, I have two questions. When you switched from the table access method to the resource manager, I assume you lost the encryption of the buffers, the shared buffers. Is that right?
Yes, we no longer encrypt the buffer.
So that didn't. Okay. And then the other question is, what prompted you to go table level granularity versus the whole cluster? Do you have separate keys for each table? I didn't understand why there was table level granularity there.
We basically went that way because that's a feature that exists in many other database servers where you can say that you want this table to be encrypted or not. And that's something that we see that's often case in real databases, like this table contains sensitive data, it has to be encrypted. This table only has some generic columns there that it doesn't need it. And it was also, if we go to table level granularity, it is also simpler to add the encryption to an existing PostgreSQL database because it already has tables in it, and then people don't want to completely take it offline, possibly for days, to encrypt everything. They want to do it slowly in some process. So this way, anybody can add our extension. Well, they also have to switch to our fork, but they cannot do our extension, and then can change tables to be encrypted one by one in a slower process.
Do all tables use the same key?
We have a two-level architecture, so we have a key that encrypts other keys, and each database object has its own key, but these keys are just stored in the database itself. And then we have one key encrypting all these internal keys, and that's stored externally in a secure server.
Thank you. Any other questions?
Is it production ready right now?
Yes.
Yes?
Yes, it's already released and usable.
And do we have to use a Percona distribution PostgreSQL server or PGDG community?
Yes, you have to use the Percona distribution because we had to add a few small patches to the PostgreSQL server itself. So unfortunately, it only works with our fork right now.
I have two questions. What about statistics? What about statistics, PG statistics view? There is some data inside?
Yes,
so
there's some data there, and that's why that's one of the remaining tasks we have to do because the system tables are not encrypted yet.
And what about PG inspect extension? Is it usable with your modification?
I personally didn't try that, so I can't answer the question for sure. I'm not sure if somebody else did.
Hello. What about the replication with Parragi, for example?
Those work properly. Replication replicates the wall, but we basically replicate the plain text wall, not the encrypted one. And that's safe because replication already happens using encryption. So it already uses an encrypted connections. So basically, Postgres internally decrypts the wall, sends the decrypted wall to the other server, and the other server probably also has encryption configured. So when it writes the wall to the disk, it encrypts it again with a different key.
Is it possible to have different keys in a replication chain? So for example, one key for the primary and another key for the replicas?
Yes, we don't enforce that people have to use the same key for not just the wall, but for any table. So different servers in a cluster can have completely different keys, can use a different place to store their keys and so on. It all customizable.
Do we have any other questions from the room? I guess you guys want 5 more minutes break. So thank you for the presentation. Thank you for amazing questions.